And first of all, Rohan Yadav from Stanford is going to give the first talk about task-based tensor computations on modern GPUs. So Rohan is a fifth-year PhD student at Stanford, working with Alex Aiken and Fred Kohlschlag. He is also a part-time researcher at NVIDIA, working with Michael Bauer and Michael Garland. And most importantly, he'll be in the job market next year. So with that, Rohan, you can take.
Okay, thanks for the introduction, Charit. Hold on, let me start my timer, make sure I'm on time. Okay, so hey everyone, I'll be telling you today about a different way of writing tensor computations on the crazy GPUs that we at NVIDIA have been building. So, well, if you look at GPUs over the past couple of years, despite the end of Moore's law, our GPU, we have these beautiful marketing diagrams that show performance continuing to go up, despite our cores not actually going that much faster. And the main reason for this is, one of the reasons is due to specialization, in particular the introduction of tensor cores, which started back in 2016 in the Pascal era GPUs. So what is a tensor core? Well, a tensor core is all it is just a little instruction that the GPU provides to do certain kinds of matrix math faster. So on the Pascal architecture, this started off really small, where a single thread could say, hey, I want to do a 4x4 vector dot product, and you would get that done for you a little faster than the normal set of instructions. This became a bit more complicated in the Volta architecture, where you actually had a matrix product now. So you could do an 8x8x4 matrix multiply. But the caveat was that now you had to have 8 threads cooperate to do this multiplication. So your inputs and output would have to be sharded across all of those 8 threads. Again, this became a little more complicated in Ampere, where you now are doing a 16x16x8 multiply. But the complexity increased too, where now 32 threads had to share the inputs and outputs of this multiplier. This has reached a crazy inflection point in the Hopper GPU, where you have a humongous tile size, in particular 64x256x16, and now 128 threads have to all cooperate to use this beast of a tensor core. And this thing is so big and fast now that NVIDIA had to add a data movement accelerator called the TMA to make sure data could move fast enough to actually feed this tensor core. So I showed you a scary picture here, but what does this actually mean for the kinds of programs we want to write? Well, I'm going to argue that this is fundamentally changing the CUDA programming model. So I've shown up here some code that you would use to write a GEMM-like computation for GPUs before Hopper. This looks something like a classic Atlas-style BLAS, where you're decomposing your computation into tiles, and then it was written in a very bulk synchronous way. Kind of, you don't have big accelerators, so all your threads have to cooperate in loading some data from global to shared memory, loading some data from shared memory to the registers, and then actually doing a GEMM. And the thing that was good about this was that your compiler and your hardware did a lot for you to actually overlap all of these stages. The hardware would make sure that all these loads were happening on different units, and then the math was happening separately from those from the loads. In Hopper, this has changed a lot. In particular, now that we have all these big accelerators that do a lot of stuff for us, we get something that looks much more like task parallel code from this bulk synchronous stuff from before. So in particular, your code now has to be warp specialized, meaning that some threads are going to be responsible for invoking this asynchronous data mover called the TMA, and then a separate group of threads will be responsible for actually invoking this tensor core. These things are going to communicate through basically shared memory barrier objects, kind of poking each other to wake up and go to sleep back and forth. And then these accelerators themselves are now asynchronous, meaning that you invoke them and they return immediately. But then to actually check when it's done, you have to start polling some flag in the background that tells you when this copy is done or when this matrix multiply is done. And even more annoyingly, the tensor core is a separate processor on the chip now, so then you need to actually find work to do to fill your normal floating point units while the tensor core is running. And so in some ways, this whole software pipeline of writing a GEMM has gotten easier because the architecture became more complicated. But at the same time, the difficulty switched, where now we have to write this task parallel asynchronous code, and humans have been historically terrible at doing this. We are not able to write code like this very well. So I think our programming systems, like we at PLDI, need to evolve to face these kind of challenges. And I think there's several trends that are all colliding that make me very scared as a programming languages researcher. So first, there's this proliferation of these on-chip accelerators. Kind of, we have this data mover, we have these matrix multipliers. And so as the set of things we think are important continue to change, we're going to get more and more of these accelerators. And then there's going to be this difference where every time we add some more accelerators to our chip, we have to keep changing the code we write. Like I showed you, the code was so different between before Hopper and after Hopper. Then there's this pervasive asynchronous programming that is starting to hit our programming systems, where everything is asynchronous as these hardware units get bigger and bigger, and they require really deep pipelines to keep them fed. And so this code has to be both high performance and asynchronous, something that is hard, it has to be correct and fast. And getting both of these things at the same time is known to be quite difficult. The real nail in the coffin, though, is that everybody wants to write their own programs for these devices. You know, we can't just hide behind BLAS anymore, because everyone wants to write a custom kernel for their custom neural network. And so we have this that, we have more code, it's getting harder to write, it's changing over generations, it's asynchronous, and has to be really, really high performance. So this is a very scary combination of things. So what we wanted to do in this work was to provide automation for a lot of these low-level, difficult things to do, but instead leave a lot of control for people who know what they're doing to get high performance. And so what I want to give to the programmer is a programming model that has sequential semantics, meaning that I want to automate away things like dependence analysis, data movement, synchronization, and concurrency. But I think it's really important to retain explicit control over things like how your data is partitioned amongst your GPU. Where does the data live in the GPU memory hierarchy? And the ability to exploit architecture-specific capabilities. If you look at the programming systems that we have today, you kind of get one or two of these things. If you have systems like cuBLAS or Thunder Kittens, basically they don't really do that much for you to help out with these difficult parts of writing the code, but you are able to write that beautiful sequence of instructions that gets 100% of peak on the machine. So you can get that high performance, but you don't get too much help to make sure your code is actually correct. Or you have systems like OpenAI Triton or the recently released CUDA Tile, where you get a very nice sequential-looking programming model. These tile-based models are great, but you don't get to control these other things at the bottom. In particular, your compiler has a bunch of heuristics to decide what to do here. And I'll show you there are many cases where a compiler does not do the right thing, and you as a programmer have no way to tell the compiler what you know and want to do in your program. So in this talk, I'll talk about one way that we can get both of these things, and by picking what I think are good abstractions, we can get both automation of difficult things and get really high performance code. So I'm going to talk to you today about a system that we built called Cypress. And so Cypress, you write programs in Cypress, they have two components. The first is a logical description of the computation, which is a task-based parallel program with sequential semantics. Then you write separately a mapping description of the program, and this is going to specify a variety of performance-sensitive decisions that you actually will bind your program onto this physical machine. So I'm going to talk mostly in this talk about Cypress programs, and if you want to see about a compiler, you can go check out the paper. Okay, so let's talk about what machines look like and how we model them, because that will motivate the kind of programs we want to write. So the GPU is a very hierarchical machine, and we're going to model this pretty directly with the hierarchical structure of the processors, where you have processors that describe different levels of this machine, such as the host that actually launches GPU kernels, blocks that run on SMs, warp groups, warps, and threads. And then you have different memories, like the global memory, which every processor can access, the shared memory, which is visible to only one SM, or the registers, visible to individual threads. So you have this hierarchical machine, and basically we're going to write programs that decompose both our data and our computation across the processors and memories of this system. Okay, so here's a little component of a Cypress program that computes a GEMM. And so we're going to first just explain the syntactic structures in this piece of code, and then we'll put them together to kind of interpret the program. So a Cypress program is written as a collection of tasks. So this is the GEMM task. And every task has a set of variants. You can think of a variant as a concrete implementation of a task specified for a particular level of the machine hierarchy or for a particular algorithm. These task variants can either be inner or leaf variants. This particular task is an inner variant. And so inner variants get to launch more tasks. They get to decompose their data and decompose the computation for more recursive structure. They can do this in a few ways. One of them is with this p-range operator, which is going to launch a parallel group of tasks that don't interact with each other. Or the s-range operator, which is going to launch a group of tasks that must execute one after the other. We have leaf tasks, which you're not actually going to see in this talk, but they're actually going to execute concrete computations, like launch some work onto the Tensor Core or do some floating point math. When we talk about data, every task is going to take in a set of tensors, and then they're going to describe to the compiler how they actually use those tensors. So for this GEMM program, this GEMM is going to read the input tensors A and B, and then write to the output matrix C. Finally, tasks get to partition their data through a series of structured partitioning operators, such as this blocks operator, which is going to break up tensors into tiles of the given shape. So putting it together, what does this program do? Well, so at the host level of my GEMM, what I want to do is I want to break up my matrix, my output matrix into tiles, construct panels of A and B that each tile needs, and then launch a bunch of parallel work, where each subtask is going to compute one of those output tiles of C. So let's look at a different algorithm, a different variant that you might choose for a different level of your machine hierarchy. This is the block level variant. So now running on an SM, you have shared memory and registers to exploit, so some locality to use. So for this particular algorithm, I'm going to use a different choice, where instead I'm going to create an accumulator tensor, and I'm going to break up my k dimension of the iteration space into chunks. And then what I'm going to do is I'm going to initialize my accumulator. I'm going to then loop over the k dimension in pieces, launching gems that accumulate into my accumulator. And then finally, I will copy that accumulator back out into the output tensor. And I want to emphasize here, I've shown you two test variants. And note that this code is sequential. There's no explicit data movement. There's no concurrency. All of it is going to be done by the compiler. And here we're just structuring a program that says, here's the logical algorithm I want to run. OK, so let's talk about then binding this program onto a real machine. So the mapping description is where we're going to encode a lot of performance-sensitive decisions. We can do things like say at a particular task call site, what variant should run? What processor should that task run on? What memories should it put all its tensors into? Then we can also specify a variety of tunable decisions, kind of hooks into the compiler. Things like what block sizes to use, how deep should you software pipeline this loop, and so on. So concretely, you can say things like, I want this task in the task hierarchy to put its tensors in shared memory, and these tasks lower to put their data into the registers. And the compiler is responsible for moving the data and maintaining synchronization as these mapping decisions change the program. So the Cypress compiler is going to take these two things in and output you some code in the cute C++ library that actually runs on your GPU. And it has got a bunch of passes that you can check out our paper for more details. But at a high level, these passes are going to lower away tasking abstractions. And then they're going to perform optimizations to actually bring that code closer to what an expert would write. So the first result I want to show you is that first, our compiler infrastructure can lower these Cypress programs into high-performance code. So for important computations, like GEMM or batch GEMM, we can get code that is very competitive with cuBLAS. That's kind of expected because we know exactly, these systems are built by the expert engineers, and we know the decisions that went into making those high performance. A more interesting part is that when you're trying to compare against high-level systems, the control that Cypress gives you enables you to do better than these high-level systems when their heuristics fail. So for computations like this dual GEMM, you're fusing two unrelated matrix multiplies together, or this GEMM plus reduction computation, where you're going to do while you're doing a GEMM, you're kind of performing a streaming reduction on one of the other tensors, being able to control things like, hey, I want to put the reduction output in the registers rather than in the shared memory, which Triton does, can be the result of a significant performance difference on this machine. And so, you really there's a lot of benefit to turning the compiler inside out and being able to give these decisions as you know them rather than having it figured out for you. I think the most interesting program we've written in Cypress is Flash Attention 3. And so if you don't know about Flash Attention 3, I don't want you to actually read this code right now. But the basic idea of Flash Attention 3 is that it was an implementation of this key flash attention algorithm for the Hopper GPU. So they kind of had to redo a ton of stuff in the algorithm to perform well on Hopper, taking advantage of all of these asynchronous features of the architecture. And so if you look at this code, there's a ton of stuff that I don't like here. Things like wait for this thing to be loaded in shared memory. Launch this WGMMA, but commit it and don't wait. Launch this thing, but do wait. And in fact, if you look at all this code, it is more than the actual algorithm of flash attention. And I want to make the case that if you program in a language like Cypress, where we take seriously our compilers should not have make people deal with this, like all of this code goes away, and you write something that looks more like the actual math you want to do. And I want to also emphasize kind of a more to call an action. The main thing that Flash Attention 3 does, if you know about it from Flash Attention 2, is a software pipelining transform on the main loop. And kind of if our compilers were better, we could have done that automatically rather than waiting for 3 years architecture to come out and get it. Like, we should have been able to do that by ourselves. OK, so coming back to the main point, we can automate all of that data movement and synchronization, but still get code that compares well with the handwritten Flash Attention algorithms. So with that, I'm going to conclude and leave you with a few thoughts that I really believe, especially from my background in actually writing distributed programming systems, that things like communication and synchronization should be the language implementation's problem. Like, these are hard things for people to get right, and our compilers have a lot of knowledge of how to deal with that things. And so I showed you today how a set of abstractions, particularly task-based abstractions, that are one way that we could actually make this a reality. And I showed you how we can use them to express high-performance Tensor Core computations and run efficiently on modern GPUs. With that, I'll conclude, and I'm happy to take any questions. Find me offline. Love to talk about Tensor Cores.
Right. I have one question. So you implemented flash attention, right? So flash attention has this kind of softmax accumulation that is not correct in the intermediate stages, but finally it cancels off, right? Mm-hmm. So how did you implement that, specifically?
Well, I mean, we have the difference in our programming system. We're not starting from like a high-level, really high-level algorithmic description. We're starting from a description where you say, here are the tasks I want to run. And so those tasks are allowed to do, those tasks are written in a way that say, I want to do the softmax reduction and just put the data here. Like, we're not leveraging semantics of the linear algebra. We're just leveraging semantics of saying, this task will read to some data, this task will write to some data. Therefore, these tasks need to run in a certain order. So we could just, we write down the flash attention, but we kind of copy this algorithm description into the code. And so we don't recover that accumulation, we just do what it's said to do.
Yeah, I had one more question. So in the results, there were few slowdowns. Could you explain what were the reasons for those?
Yeah. So this particular, I mean, the main reasons where we're a bit slower in the flash attention algorithm is we don't yet implement this particular optimization called the persistent kernel optimization, where you have where basically you launch a fixed number of thread blocks, and those thread blocks sort of grab work that they want to schedule. So you basically, at small problem sizes, you avoid certain overheads in setting up and tearing down CUDA kernels. You could presumably do that in our model, like a p-range loop over your blocks doesn't have to turn into a thread block with that same width that could be implemented by a set of blocks that are scheduling themselves. Yeah.
Hi, this is Rohan from NYU. So I personally don't have a lot of knowledge about these compilers for GPUs, but if I remember correctly, Thunder Kittens was one that allowed you a lot of low-level kind of control over things, but didn't give you these nice abstractions. And yet, it seems like Cypress outperforms in some cases, like in longer sequence lengths, even Thunder Kitten. So can I ask, where do these extra performance benefits of Cypress come in? Like, how is it able to do even better despite being higher level?
Yeah, so first, I mean, one thing is that Thunder Kittens, at the time of writing, Thunder Kittens, they had only implemented Flash Engine 2 in their things. So there's a slight algorithmic difference. You'll know that actually you can reconfigure the system. You can kind of reconfigure these algorithms to actually perform very similar to Flash Engine 3, which is a separate thing. But there are a lot of small differences, I think, inside the actual just generated code. Like, we're at the level that individual cycles tend to matter. And so they wrote their own infrastructure for interacting with the Tensor Cores. I was reusing stuff that NVIDIA built. I mean, you can imagine there are small differences in that exact generated code there. I think fundamentally, if you at the high-level C++ code that's generated, they're mostly the same. And I actually, I looked a lot at those blog posts. They're very good to help me learn about the space. Yeah.
Quick question. All right. If not, let's thank the speaker again.